Because regular functions, they don't, I mean, I don't intend on allowing this. Regular functions, you can't pattern match on the function. It won't just remember all of its arguments. So we have to rework this somehow. And I think the most sensible way to rework that is to say cons. We'll keep these two. These are part of making the type signature. But what we'll say is it's a primitive. For good measure, we'll put the type of the primitive here. And it's a primitive on a value of type A and a value of type vect AN. All right, so this time, and then nil is sort of similar. Nil becomes a function from A, and it's a primitive of type vect A0. All right, okay. So then if we wanted to write our VS, right, we'd say VS is the cons. And we're going to keep the type of cons the same. This will be the same, this type. The only difference is when we expand the definition, we'll run into this primitive term. So we know to fill in each of the primitive slots, right? We'll fill in the first and then the second one. But the type will be the same. It'll just be this function. So we'll say this is n, 1, 7, the element we want to put on, and then nil, n, like that. So now if we want to match on VS, well, the expansion of this, if we expand this out, this is a primitive which holds 7 and nil, which is another primitive. All right, so this primitive is of type like vect n1, and then this primitive is of type vect n0. But now when we match on VS, it's a primitive that holds these typed holes here. So we can then expand it out and we don't have a problem. Okay, fantastic. This seems like a solution to the problem. But I don't like these types being defined by being open, because anyone can add a new primitive. So if you match on a specific vector like that, the specific vector is like a cons or a nil, right? It's either got a nil or a cons. Or, well, okay, let me be more explicit. If we match on a specific vector, if we match on this specific VS, it is a cons. There's no doubt about it. It's a cons cell. And then we can destructure the cons cell. But what if we don't know the vector? So can I get a new page here? Yeah. So where's my, here it is. So all we know is that VS is of type vect, I don't know, we'll stick with the natural numbers and it's 20 long. So if we match on VS, or no, let's even be more generic. Let's give a more realistic example. If we want to write the function map, all right, so map, whoops, it's going to take a type, it's going to take a natural number, it's going to take a function from A to B, then it's going to take a vect an and give back a vect bn. Okay, so now if we tried to define map, right, what would that look like? Well, firstly, we'll take in our u0 and our n and our f. and our vector. All right. And then what we want to do is we want to match on VS, right? And we want to break out the various cases. So the ideal case, if everything works, is we can see it's either a cons cell with like an A and I don't know, A's, whatever, or it's a nil. So in the nil case, well, let's do the cons case first. In the cons case, what we want to do is we want to do a new cons of type B. We kind of need to match on N as well, unfortunately. Okay. I'll add that in. So we want to match on VS and on N. And in this case, we have a cons cell and a successor cell. In this case, we have a nil and 0. Like that. So here, what we want to do is we want to cons A M FA with map A M F A S. And in this case, we just want the answer to be nil, whoops, but of type B instead. Okay, so this sort of logically, okay, this is fine. But the main problem is when we do this pattern match, this map function is not working with a specific vector, right? It's just some variable. Right? It's not a specific vector defined in terms of cons and nils. It's just some variable. So when we pattern match on it, we need some way of knowing that the only two cases are cons and nil. And if we define our functions by this kind of open, we just define our types rather. By this open, we just define the type, and then any primitive of the type just becomes automatically added to the type. The problem is that anyone can add to the type. So we write a nice little vector library like that. And then someone else comes along and goes, well, you know what? I think there should be a new kind of vector type. I'm going to call it, I don't know, a reverse vector or something. It doesn't really matter. And the way that a reverse vector is going to work is you're going to take your A of u0, you're going to take your N of N, and we'll take a vector of AN, and you'll still have a vector of AN. But this is going to be a new primitive in the vector type. VS vect AN. And then we will define, not quite. And then we'll define this as a primitive of type vect AN, and we will accept a vect AN. So for whatever reason, the person who does this is saying that if you have a vector, a reverse vector, well, I guess technically that would be something like reverse N 1, then we'll just go nil N. The reverse nil? Whatever. This person is saying that this should be a primitive. And now if we come back here, well, we should have technically a third case now. We should be matching on rev, I guess. Rev XS and I don't know, M. and we should be doing stuff here. So this will break every single function that matches on vectors ever, like anywhere. So we don't want that. we don't want to allow anyone to just add new primitives to our function types. Also, it's slightly awkward to extract all the primitives because if you look at rev is not like strictly a primitive. It's actually just a function which returns a primitive. So it's a little bit awkward to really figure out like, hey, what are all the primitives that we should be matching on? Because you need to go through all your function definitions and find any primitive that is of this type. But that's also weird because, vect itself is not really a type. It's a type family, I guess, from A to N. So the task of matching up all the primitives to all the types they come from is actually slightly finicky. And you can imagine constructing cases whereby the label primitive appears somewhere, but it's not possible for it to exist. Right? So like if you have a function f which goes from the empty type to vect or a and whatever, just abusing notation. Then lambda x of type empty, and then this is primitive, and whatever, it's got the type. Doesn't matter. Even though this primitive appears here, and so if we were just walking the tree to find every primitive, we would see a primitive and go, it's of this type vector. This primitive can never actually be constructed. Like, you can never match on it. Now, that's strictly not the end of the world. Like, you could still have your case analysis here, and you would just have to match on, I guess, F. You would just have to match on F, and this branch could never be taken. So you might as well do that. This branch could never be taken because this primitive can never be constructed. But it is... it's not very aesthetically pleasing. It's not very nice that this is possible to do, in my opinion. So, what are we going to do about this? Well, as I mentioned, I was reading through these papers, and he talks somewhere. It might be later on, but he goes through somewhere, basically defining these as special cases. Well, not just these, actually defining a lot of types as special cases, where he writes out a kind of schema like this, and he says, we're special casing these for a general version of the same thing. Go see his older paper. So okay, I went and found his older paper. And what does he do in his older paper? So in his older paper, it looks like this. So if we're doing the vector type, right? So vector, we'll do its type signature first. Is that right? Do we do its type signature first? We'll do its definition. So vector, it's going to take in an A from U0, it'll take in an N from N. And then what we're going to do is we're going to return a type signature that is the type of vector. So I guess vector's type is from U0 to N to U0.